Welcome to ScaleUp University. Welcome to the course on building applications with AI agents. So this is the lecture 16 of module 1, and in this lecture we will be discussing foundation models and multi-agent systems. So first let us look at the lecture overview, like what we will be discussing in this lecture, what this lecture is about. Foundation models and multi-agent systems. So see, we already saw single agent systems, and we realized that single agent systems are powerful, and we also got an idea about multi agent framework in the previous lecture, and we realized that multi agent systems are even more powerful because we are talking about collective intelligence. We are achieving collective intelligence, but multi agent systems, they are powerful only if coordination works. So multi agent systems, we have some challenges, like there should be coordination. So if coordination is there, then multi-agent systems are powerful. So the central question we will be answering in this lecture is, how do multiple autonomous agents work together without chaos? So this lecture is about coordination among multi-agent systems. So in this lecture, we will be discussing how multiple autonomous agents can work together without chaos. And the answer to this question lies in foundation models. So foundation models, like the large language models, they act like they perform orchestration. They act like orchestrator, which is enabling coordination among autonomous agents. So the answer, like how do multiple autonomous agents work together without chaos? The answer lies in foundation models. The answer lies in structured communication, and the answer lies in orchestration layers. And that is what we will be discussing in this lecture. And this is where agent systems, they move from isolated intelligence to coordinated intelligence. And that is what we will learn in this lecture. So this lecture is about coordinated intelligence, like coordination among multiple agents, coordination in multi-agent systems, and how they make use of foundation models to achieve that coordination. That is what we will be discussing in this lecture. So if we look at the topics that we will cover in this lecture, so in this lecture we'll talk about relationship between foundation models and agents, agents working together, coordination via language, context sharing, collective reasoning, planning at the system level, why orchestration becomes critical, shared versus independent models, failure modes in multi-agent systems, when multi-agent systems excel. So all these topics we will be covering in this lecture itself, one by one. So this is the module 1, introduction to agents, lecture 16, foundation models and multi-agent systems. And we will be starting with the first topic of this lecture, that is relationship between foundation models and agents. So foundation models, that is the large language models like GPT-4, Claude or Llama 3, they serve as the cognitive engine. So that is like the brain. Foundation models, they are like the brain, cognitive engine. So foundation models, if we talk about, they provide language understanding. So foundation models, they move beyond keyword matching to grasp nuances, intent, and sentiment in language. So foundation models can very easily understand the language. So that's very powerful. Foundation models, they provide reasoning capabilities. So through chain of thought, foundation models can break down a problem into logical steps. Foundation models, they provide planning assistance. So foundation models, they can suggest a sequence of actions to reach a desired state, identifying prerequisites and potential hurdles. And foundation models, they provide context interpretation. So foundation models, they maintain high dimensional representations of information, like the context, which allows the foundation models to understand how a specific word or fact changes meaning based on the surrounding data. So foundation models, they can maintain the context, they can manage the context, and they can interpret the context. So with the power of context, they can learn on the fly. They can keep on evolving, they can keep on learning, they can keep on adapting, adding on new knowledge with the power of context. So this is very powerful. So foundation models. Now, if we talk about agents, what agents do is they wrap these capabilities with. So agents, they make use of foundation models. So since agents make use of the foundation model, agents, they acquire the capability of language understanding, reasoning capabilities, planning assistance, context interpretation. So agents, they can understand natural language. Agents, they can reason. Agents, they can do the planning, and agents, they can like evolve. They can learn on the fly. They can keep on adding new knowledge. And along with that, agents, they are equipped with even more capabilities like goals. So every agent will have a goal. So agents, they work to achieve a goal. So agents have goal driven behavior. So every agent is associated with a specific goal, a specific task they're trying to accomplish. Agents, they have memory, like both short term memory and long term memory. So short term memory is the context window, and long term memory is like the vector databases, RAG, retrieval, augmentation, generation. So memory allows the agent to learn from previous steps. Agents, they are equipped with tools like external APIs, databases, or functions. So the agents can decide to use a particular tool like a calculator or search the web or write to a file. So see these tools, this gives the agents the ability to take actions, because foundation models, they are passive. They can generate response, but they cannot act. But agents can act. So agents are intelligent because of foundation models, but they can even act also because of tools. They can execute the tools. So they can perform actions in the real world. And that's what agents have: execution loops. So they follow the think, act, observe cycle. So the agent evaluates its own output, checks if the goal is met, and try again if it failed. So in multi-agent systems, so multi-agent system means we have a system wherein multiple agents are operating. Now these multiple agents, they might have their own model, meaning to say that each agent will have its own model, a separate model. So each agent has its own foundation model. That is one of the possibility. Another possibility is the shared model, wherein multiple agents, they will share a common model. So here we can see this is the foundation model, and both the agents, they are sharing the common foundation model. And we can have specialized models assigned per agent or per role. So let us suppose we have an agent which is assigned a role A, like content creator. So now it will be given a specialized model. Similarly, let us suppose I have role B, that is a uh, coder. So it will be given a model which can generate efficient codes, which can write code. So that's the idea. So this is very clear that okay, in multi-agent systems, we can either have like each agent can be equipped with their own model, or each agent with specialized role can be equipped with specialized model, and agents can share the model. Now, if each agent is equipped with its own model, it is best for high privacy or autonomy, because if we want that agents they should work independently, and so some privacy concern is there, then it's good that each agent should have their own model. So that scenario is good for high privacy or autonomy. So each agent will having its own model. So in the sharing model, shared model, wherein multiple agents are sharing a common model, it is the most efficient for resource management, because multiple personas can call the same API but are given different system prompts. Like the same model for one agent, it can act like a coder. The same model for another agent, it can act like a reviewer. So here we are making the efficiently using the resources. And the third model, specialized models, wherein every agent will be provided with a specialized model. So here we might use a heavy reasoning dense model for the manager agent, and a fast cheap model for the worker agents. So it gives us more flexibility. So foundation models, if we talk about, so here we understood the importance of foundation models. So the idea is that in multi-agent systems, foundation model plays a very important role, and that is what this topic, this slide is about: relationship between foundation models and agents. So agents they make use of foundation models to understand the natural language, to reason, to plan, to interpret the context. And in multi-agent systems, foundation models plays a very important role. So foundation models, it enables flexible reasoning within each agent and meaningful communication between agents. So with foundation models, each agent can like do flexible reasoning, and agents can perform meaningful communication. Without foundation models, if there was no foundation model, then the coordination among multiple agents, it would have required rigid rule-based protocol. And rigid rule-based protocol, they fail because the real world is very uncertain in nature. It is stochastic, probabilistic. So rigid rule-based protocols will not be able to survive. That's the idea. Agents working together. So when agents they collaborate, they work together, they share goals. Because in multi-agent environment, multiple agents they are working in collaboration, and interestingly, all these agents they share a common goal. So agents they ally on a global objective, because the entire system is working towards accomplishing a common goal. While an individual agent might focus on a subtask, its logic is guided by the overarching mission, that is the completion the completing the global objective, to ensure its output is relevant to the final result. So idea is very clear: in multi-agent systems, every agent they are working independently, they are accomplishing some small goals, but that small goal is aligned towards the main goal which the system is trying to achieve, which the system is trying to accomplish. So in multi-agent systems, agents they collaborate, they share goals, they divide tasks. So in multi-agent systems, there is a manager agent, or any central logic loop which acts like an orchestrator. What it does is that it knows the main goal to achieve, and it breaks that goal, like it like come up with task, set of tasks to achieve that goal, main goal, and it distributes it among multiple agents. So in multi-agent systems, the agents they collaborate, and the task it gets divided. among multiple agents, and all those agents, they accomplish their subtask, and when they do that, the common goal, the main goal of the system is achieved. Exchange context. So in multi-agent systems, agents, they collaborate and they exchange context. So unlike humans who might forget details, agents pass state to one another. So that is the exchange context. So agents, while they communicate, they can also pass the state to one another. So this includes metadata, previous tool outputs, and summaries of what has already been discovered, ensuring the next agent does not start from zero. So this is very important. So when agents collaborate, they also coordinate actions, like, and coordinate actions, like, it governs the sequence. So agents must know if they can work in parallel or if they must work in series, because this coordinating action is very important, because there might be some tasks which are dependent on other tasks. So if the other tasks are not performed, then there can be coordination problem. Dependency is there between the tasks. So in multi-agent systems, agents, they also coordinate actions. So that's also something very interesting. And when agents collaborate, they also resolve conflicts. Because in multi-agent systems, we can see conflicts wherein when two agents produce contradictory data, or if a tool fails, the system uses refinement loop. So an agent might say, agent A's data contradicts the compliance check, then agent B can verify it. So whenever there is any conflict is there among agents, like conflict because of any contradictory data, or if a tool got failed, so that conflict they resolve. And interestingly, to perform all this, there is a communication, there is a coordination, and multi-agent systems, they make use of foundation models. So now it's very clear that in multi-agent systems, multiple agents, they are working together, they are collaborating, they share goals, they divide tasks, they exchange context, they coordinate actions, they resolve conflicts. Let us look at one example of a multi-agent system wherein multiple agents, they are working together to accomplish a common goal, the main goal. So let us suppose in a multi-agent system, we have one agent which gathers information. So agent gathers information, that agent analyzes the information. So we can have another agent, like one agent is responsible for gathering the information. Now whatever the information it gathered, it will send it to the any other agent. That agent will analyze it, and insights it will share it with another agent. That agent, agent 3 will generate recommendations and share it with agent 4, and agent 4 will validate the compliances. So here we can see that each agent specializes. Like agent 1 is specialized in gathering information, agent 2 is specialized in analyzing the data, agent 3 is specialized in generating recommendation, and agent 4 is specialized in validating compliance. So each agent specializes, but success depends on coordination. So this is very important, that in multi-agent systems, coordination is very important, because we have specialized agents in place. But if there is no proper coordination, then things may go wrong. Proper coordination is very important. Proper coordination among agents is very, very important. And interestingly, foundation models helps in establishing that coordination. Coordination via language. So one of the most transformative aspects of foundation model is language. Like the natural language, it becomes a universal coordination protocol. So this is very interesting. So the idea is that because of the foundation models in multi-agent systems, multiple agents, they can coordinate with each other using natural language. That is very powerful. So instead of hard coded message formats, instead of complex logic symbols and instead of rigid communication rules, these agents, they can communicate through structured natural language. They can describe plans, they can explain reasoning, and they can ask clarifying questions. So because of the foundation model, now agents for communication, for coordination, there is no need for agents to follow any hard-coded message format, complex symbolic logic, or rigid communication rules. Rather, because of foundation models, in multi-agent systems, multiple agents, they can communicate, they can coordinate through structured natural language. That is very powerful. They can describe plans, they can explain reasoning, and they can even ask clarifying questions because of foundation models. Because the idea is that, let us suppose a agent got a message from any other agent and that is bit ambiguous. So now in natural language interface, agents can ask clarifying questions. If they are facing any issue, they can clarify it. They can even describe plans, explain reasoning. But in rigid communication rules, all that is not possible. So here, the natural language, it acts as abstraction layer. It acts as a flexible communication channel, and it acts as a coordination medium. So natural language becomes a universal coordination protocol and foundation model. And because of foundation model, and this drastically reduces integration complexity. And this makes coordination in multi-agent systems relatively simple. And hence, if I talk about multi-agent systems, I can keep on scaling it. I can keep on adding more and more agents to it without introducing much complexity. And because of the foundation model, each agent is intelligent. They can very smartly handle, because foundation models, it has the complete idea of all the agents present. And if one agent is down, fault tolerance, resilience is taken care by foundation model itself. Let us suppose we are trying to get a response from an agent, that agent is down. Now foundation model, it will automatically tell where to route the request, because it knows what all agents are present. It is aware of the current state. So that's the idea. Coordination via language. Context sharing. Now see, context sharing, it is the foundation of collaboration, because for collaboration to work in multi-agent systems, when agents are coordinating, they are working in collaboration. Context sharing is very important. And what is context sharing? Context sharing means, let us suppose agent A, it is working towards accomplishing a subtask. Now, whatever steps it took, whatever output it generated, that is the context. Now, while it is sending a request to agent B, it can also share the context. It can share its finding. So that's the context sharing. Now, context sharing, if I talk about, it includes current task state. So whatever the current task the agent has performed, so it can share that current task state. So it involves which sub goals are finished, which are in progress, and who owns what. So current task state is about the progress of the task, like which sub goals have been accomplished, which are in progress, which are pending, and so on. Partial results. The partial results is the intermediate data findings. Assumptions. So this is very important, assumptions. So the idea is that, let us suppose agent A assumed something while reasoning or while accomplishing a subtask. That assumptions, it will share it with agent B. Now that assumptions may be related to the environment model, beliefs, So whatever assumptions the agent A, for example, made while accomplishing the subtask, when it will be sharing the result or the partial result with agent B, it will also share the assumptions which it considered. Constraints. So context sharing, it also includes sharing of constraints. Constraints are the boundaries, like the deadlines, resources, safety rules, that's the guardrails, budget limits, character counts. Do not use X library. So let us suppose agent A, it is working towards accomplishing a small goal. So it might be subjected to some guardrails by the user or by the system. Now, when agent A will be sharing the context with agent B, it might also share that constraints. Agent A might tell agent B that you have to follow these guardrails and observations. So context sharing, it also includes observations, wherein we have an agent which is responsible for perception, like perceiving the environment, getting the input signals. So real world feedback from tools or the input itself. So sharing of that is also context sharing. So now it's very clear that when we talk about coordination or collaboration in multi-agent systems, so multiple agents they are collaborating with each other. Context sharing is the foundation, wherein agents they can share the current task state, they can share the partial results, they can share the assumptions, they can share the constraints, and they can share the observations. Now there are multiple approaches for context sharing. So we can have shared memory state or shared memory store. So idea is that, like in multi-agent system, all the agents they have access to a shared memory which is acting like a blackboard or a slate, wherein all the agents they can write over it and other agents can read it. So all the agents they can write it, they can read it. So we have a shared memory store, and with this context sharing can be done, because agent A, let us suppose it wants to communicate some interesting facts, some partial results it got. Now it want to share it with multiple agents in the system. So what it can do is that partial results it can directly put it in the shared memory store. So by default that will be accessible to all the agents in the system. So context sharing we were able to do. So this shared memory store, it is a fast concept but complex coordination. Then we have message passing systems. So in message passing systems, there is a direct communication. Like agent A will directly send the context to agent B, for example. So it is flexible, but it can be like it can get complex. Then we have central orchestration layer. So this is very important. So in multi-agent system, we can have a central manager or a central coordinator agent. We call it the central orchestration layer. So that coordinator agent is responsible for all the coordination. So the idea is that agent A wants to send a context to agent B. Agent A will send it to coordinator agent and tell that please pass it to agent B. Or agent A will share the context with coordinator agent, and coordinator agent will decide whom to share that information. Like the partial results of agent A. Agent A is working on accomplishing a sub goal. In that, it was able to achieve some partial results. Now it can share it to the central orchestration layer, and central orchestration layer can decide whom to forward that partial result, either agent B, agent C, agent D. So that's the central orchestration layer. Now the drawback of it is the single point of failure. Single point of failure is the drawback, because if the coordinator agent goes down, the system will collapse. And the positive side, good control you will have. And we can also share the context via decentralized peer-to-peer, wherein no central orchestration layer will be there, rather peer-to-peer communication will be there, and context will be shared among the peers. So it is a resilient approach because no single point of failure, but it is complex, it is harder to manage. Now see, poor context sharing, if we talk about, it can be dangerous. It leads to duplicate work or wasted efforts. Because see, when we have poor context sharing, what will happen is that it might happen that two agents spend money or tokens searching for the same data. So we call it duplicate work and wasted efforts. Because of poor context sharing, it can lead to inconsistent decisions, confusion in the system. Like agent A writes a creative story while agent B, the editor, thinks it's supposed to be a technical manual. There was a confusion. Poor context sharing, it leads to conflicting actions, chaos. One agent tries to delete a file while another is still trying to read it. So that's a conflicting action, chaos. On the other hand, well managed context, it enables coherent collective behavior. Because if the context is well managed, then there will be very strong collaboration in multi-agent systems, and we will be able to achieve synergy, collective intelligence, coherent collective behavior. Collective reasoning. See, collective reasoning, it occurs when multiple agents, they contribute insights. So instead of a single model trying to be a jack of all trades, we have multiple agents which bring specialized lenses to the data. One agent might be focused on mathematical precision, while another might focus on linguistic nuances. So when multiple agents, they are working together, every agent is specialized in a domain, and they will get the insights. So multiple agents, they will contribute in the insights. Every specialized agent will give their insight to a particular scenario. Collective reasoning occurs when decisions are refined iteratively. So this is very powerful. So in multi-agent systems, one agent will be responsible for creating the first draft. Then we might have an agent which might review the draft, and any problem it found, it will once again send it to get it corrected. Once again, it will review, and now if it is convinced, it can send it to any other reviewer. And if he is not happy with something, he can once again send it to the agent which will be doing the corrections. Like that, there will be many iterations until we finalize it. So decisions are refined iteratively. So collective reasoning, it occurs when multiple agents, they contribute insights. In multi-agent systems, decisions are refined iteratively. Disagreements are resolved because in collective reasoning, disagreements might be there, and there should be a mechanism to resolve it. So in multi-agent systems, what happens is that conflict is a feature, not a bug. So the idea is that, let us suppose any conflict is there among agents, there should be a mediator agent which should resolve the conflict. We should find the middle ground. So in multi-agent systems, collective reasoning occurs when consensus is reached. So consensus plays a very important role because some decision needs to be taken, and it will be taken only when all specialized agents, they agree. That's the consensus. Ensuring the final output has survived internal scrutiny. So in multi-agent systems, we can achieve collective reasoning when multiple agents they contribute insights, decisions are defined iteratively, disagreements are resolved, and consensus is reached. And this can certainly improve. So collective reasoning in multi-agent systems can improve decision robustness. And why decision robustness will improve? Because now decisions are tried and tested. Because whatever individual decisions agents took, it was reviewed multiple times. It was refined iteratively, because in collective reasoning model, decisions are refined iteratively, and hence decisions they become robust. So decisions can survive real world applications. This can improve error detection, because in collective reasoning we saw that we have a validator agent which acts like a safety net. So whatever the other agents they are generating, validator agent will validate. So error detection is there. Perspective diversity, this is very important. So we already saw that in collective reasoning framework, multiple agents with different specialization, they contribute insights. So we are diversifying the perspective. And outcome quality, this is very important. And because of all this, automatically the outcome quality will improve. The final result is a distilled version of the best ideas, which is free from the narrow mindedness or lazy shortcuts a single model might take to close a context window. Because as compared to single agent, if we talk about multi agent, there is a collective reasoning, and because of that, outcome quality will certainly increase, it will improve. Let us look at an example of a multi agent scenario. So we have a planning agent which will propose a strategy. We will have a risk agent which will act like a critic for that strategy. Then we will have a separate compliance agent which will check constraints, and we will have a coordination agent which will finalize the execution. The idea is that planning agent it came up with a strategy. Now before executing that strategy we are refining it. So risk agent it will identify all the threats, because of that strategy will refine. Compliance agent will look into whether all the compliances are filled, satisfied. So we'll refine the strategy. And once we have final strategy in place, coordination agent, what it will do is that it will distribute the task, the action plan, the set of tasks to multiple agents. So coordination agent will act like a orchestrator. So those individual agents, they will execute the subtask, and which will lead to the final execution. So the core idea is collective reasoning. It reduces blind spots. Planning at the system level. So see, in single agent system, we already saw that only one agent is involved. So since only one agent is involved, all the planning is internal to that agent. But in multi-agent systems, we saw that multiple agents are involved. So planning may occur at two levels. We can have agent level planning, or we can have system level planning. Now, what is agent level planning is, see, in multi-agent system, multiple agents are working. So each agent will plan its own actions. So in multi-agent system, in agent level planning, what will happen is that whatever the main goal needs to be accomplished, we will break it into sub goals, and we will give every agent, each agent the sub goal. Now they will make the plan to achieve that sub goal. So that is the agent level planning. We can also have system level planning, wherein there will be one orchestrator agent. What it will do is that it will make an action plan. So that is the system level planning. It will decide the coordination agent or the orchestrator agent. It will decide which agent handles which task, how tasks are sequenced, how dependencies are managed, how results are aggregated. So all these is taken care by the orchestration layer. So there can be one agent or few agents working in coordination who will be acting like an orchestrator. They have the main goal which the system is trying to accomplish. So they will break it into subtasks. They will decide which agent will handle which task, how tasks are sequenced, how dependencies are managed, how results are aggregated. So that's the system level planning. So system level planning, if we talk about, it ensures resource efficiency. Because see, the idea is that now for planning, agents, they make use of LLMs, foundation models. So if every agent is planning, every agent will be making use of foundation model. So you might like it might be costly. But in system level planning, only the orchestrator will be making use of the foundation model, because only one or very few agents will be responsible for planning. But in agent level planning, if 100 agents are there, 100 agents will be responsible for making the plan. So system level planning ensures resource efficiency. It ensures conflict avoidance. So that's very important. Because see, the idea is that in agent level planning, since every agent is involved in planning, they work in isolation and very easily conflicts might be there. Re- Repetition of task might be there. They might end up doing same things. Multiple agents might end up doing same things. But in system level planning, since one orchestrator agent is responsible for planning, there will be like very less chances of conflict. So conflict we will be able to avoid. And task alignment that we can get from system level planning. Because without it, what will happen is, especially in agent level planning system, otherwise agents will compete means they might end up doing the same task, duplicate efforts, drift from global goals. So system level planning, so the idea is very clear. In multi agent systems, we can plan at the agent level and at the system level, but we should go for system level planning. That's the right approach. Why orchestration becomes critical? So orchestration acts as the central nervous system managing the who, what, and where of the workflow. So orchestration, it is the control layer for intelligent systems. Orchestration is the control layer for intelligent systems. So if we talk about orchestration, it is responsible for assigning task. So it assigns task. So it acts as a dispatcher. Orchestration, it acts as a dispatcher, evaluating which agent is best suited for a specific sub goal based on its specialized foundation model or tool set. Orchestration is the control layer that routes messages. It ensures the right data gets to the right desk. It prevents information flooding by filtering out irrelevant noise and delivering only the necessary context to the next agent. Orchestration is the control layer that maintains global state. So it keeps the master ledger. While individual agents only see their immediate task, the orchestrator tracks the overall progress toward the user's original request. Orchestration is the control layer that enforces policies. It sets the rules of engagement. This includes security protocols. That is, agent X cannot access the financial database. It also includes budget constraints like do not exceed $5 in token cost. So orchestration is the control layer that enforces policies. And orchestration is the control layer that resolves conflicts. So when two agents they provide competing answers, the orchestrator triggers a tiebreaker logic or routes the dispute to a high reasoning mediator agent. So as the count increases, as the number of agent increases, coordination complexity grows exponentially. So without orchestrator, communication it will become chaotic. Like every agent will try to talk to every other agent, leading to token storms and redundant processing. Without orchestration, responsibilities blur. Specific steps might be ignored or performed three times by different agents. And without orchestration, failures propagate unpredictably. If one agent hallucinates or crashes, it sends bad data downstream, causing a cascade failure where the entire system collapses like a house of cards. But if we talk about orchestration, if orchestration is there, with orchestration, things will be very smooth. The system will behave coherently. So orchestration is the bridge that converts a collection of intelligent components, that is the models, into a coordinated system, the solution. With orchestration, roles are clearly defined. Each agent will have a clear job description and does not overstep its bounds. With orchestration, global objectives remain aligned. The system stays focused on the global objective, even if individual agents they encounter roadblocks or they require multiple think, act, observe loops. So this is very important because with orchestration, global objectives will remain aligned. So individual agents might slightly drift away from the sub goal or the sub task they want to accomplish, but the system as a whole will be aligned towards the global objective. So orchestration is very powerful. Orchestration, it transforms multiple intelligent components into a coordinated intelligent system. So multiple intelligent components, orchestration. Because see, the idea is that in agentic system, we can have different agents with different specialization. We have memory, we have tools, we have models. So multiple intelligent components we have. With orchestration, they will coordinate and we will get a coordinated intelligent system. Shared versus independent models. Now see, basically multi-agent systems we can design in, like there are different approaches. So we have shared model architecture wherein a foundation model is shared among multiple agents and wherein every agent will be making use of their own prompt. So all agents will be using the same foundation model. All agents use same foundation model. Roles differentiated by prompts or policies. Now, what are the pros? Simpler management and consistent reasoning. And the drawbacks, cons, it is less specialized and there can be potential bottlenecks. If I talk about specialized model architecture, here what happens is that we will be having like agents will be using different model. For example, as we can see here, model A will be used by agent A. Now this can be a specialized model. Similarly, model B is specialized in a domain 2 and agent B can make use of that. And model C might be some task specific model and agent C might make use of it. So domain specific models for task. Now what are the advantages of it? This approach, it is it will ensure optimized performance and efficient resource usage. And if I talk about cons, increased complexity and integration challenges. Because see, why performance is optimized? Because now it will be more specialized in nature. and resource usage will be very efficient, because now all the agents will not be making use of like a large language model. Some agents might end up using SLM, small language models. So we can make use of efficient use of resources. We can save cost also, but complexity will be increased and there will be integration challenges. Now, which model to choose, whether we should go for shared model or specialized model, it depends on system scale, it depends on task diversity, and it depends on cost constraints. Like if you are planning to build a small scale system, then shared model architecture is good. But if you're planning for a large scale system with wide variety of tasks, then specialized model architecture you should consider. Failure modes in multi-agent systems. Okay, now see, coordination, it introduces new failure risk like conflicting actions. Now, agent A, that is an optimizer, it might delete redundant files, while agent B, reporter, is actively trying to read them. So without a locking mechanism, the system fights itself. So it's an example of conflicting actions, because of coordination, there can be conflicting actions. There can be infinite feedback loops. It is also called as hallucination echo. Agent A makes a mistake, agent B corrects it with another mistake. Now, agent A will refine that mistake and still makes another mistake. Then agent B will correct it with another mistake. So the idea is that it will keep on going on. So it is like the hallucination echo, because we have agent A which is responsible for some analysis and agent B which is responsible for validating. So agent A does some analysis, agent B, that's a critic, it will criticize, it will give some feedback, then agent A will take it, and in that feedback there might be some mistakes. So something might happen that this loop will continue. So once again agent will do some corrections, but with some mistake still, critic will keep on criticizing. So this is the hallucination echo. So coordination, it introduces this kind of scenarios, conflicting actions, infinite feedback loops, communication bottlenecks, because coordination, it involves communication. There can be retry storms, latency, network unavailability, so like communication bottlenecks, deadlocks, like agent A is waiting for data from agent B is waiting for a confirmation from agent A. So they both will keep on waiting forever. So that's a deadlock. So system freezes in a state of mutual dependency. And diverging goals. This is very dangerous. Like over long chain of thought sequences, an agent might prioritize its subtask so much that it loses sight of the actual goal. So that is the diverging goals. So coordination in multi-agent systems, it introduces new failure risk like conflicting actions, infinite feedback loops, communication bottlenecks, deadlocks, and diverging goals. So these must be addressed. And how we can address? So these can be addressed through clear role definitions. Like we should make use of system prompts to strictly define that only the CISO agent can approve security changes. So the idea is that in multi-agent systems, we should have clear role definitions. We should have conflict resolution mechanisms in place, wherein there should be a manager agent or a mediator agent. Any conflict is there, manager agent or mediator agent should resolve it. There should be timeouts. So we should set max iteration limits before the system forces a human intervention. So timeouts are very important, because timeouts will act like a circuit breaker for deadlocks and infinite feedback loops. We can have something like 5 iterations at max. And if the system is taking more than 5 iteration, then we can call human into the loop, human in the loop. We should have hierarchical control. Like we should use a top-down architecture where sub-agents report to a supervisor rather than acting autonomously. So, so this is very important. We should use a top-down architecture where sub-agents report to a supervisor rather than acting autonomously. So the idea is that in agents also we should have a hierarchy. Like, okay, we have 100 agents. Now in the bottom level, we have 10 agents that will report to the next layer of agents. Those agents will report to next layer of agents. Like in corporates, we have CEO, like top leadership team, then executive team, then hierarchy is there. Similar hierarchy we should have in agents. Global monitoring. So we should make use of tools like Langsmith or Arise Phoenix to track the trace of every message across the system. So multi-agent systems, they require more governance, not less, because now multiple agents are working together to, and coordination is there. And whenever coordination is there, governance will play a very important role. When multi-agent systems excel, see, multi-agent systems, they're effective, they're most effective when tasks are decomposable, when we can decompose the task, when specialization improves performance, when parallelism is beneficial, when robustness is critical, and when global optimization requires distributed input. So multi-agent systems, they are especially useful in large enterprise systems, in distributed environments, in complex simulations, in collaborative knowledge work. So the key takeaway is multi-agent systems leverage distributed intelligence for complex problem solving. So distributed intelligence for complex problem solving. So finally, we completed this lecture. So in this lecture, we saw how foundation models enable multi-agent coordination, why language acts as a coordination protocol, the importance of context sharing, how collective reasoning improves outcomes, why orchestration becomes essential, how system level planning differs from agent level planning. Now, this lecture gave you a very good understanding about multi-agent systems, like you got an idea about orchestration, and now we are very curious about agent orchestration frameworks, communication protocols, multi-agent design patterns, real world architecture blueprints, like in real world how multi-agent systems work, which is like the in later part of the course we will explore all this. Advanced coordination mechanisms. So all this we will learn in the upcoming lectures in this course, like how to design multi-agent workflows, how to implement orchestration layers, how to balance autonomy with control, how to evaluate multi-agent performance. So I hope you got a very good understanding of the concepts that we covered in this lecture. So do subscribe to our YouTube channel, ScaleUp University, for more such interesting lectures and courses. Thanks for watching. Thanks for your time.